Okay, well, that takes care of the ideal gas law. Is the ideal gas law the only gas law in town? Well, no, there are a few others. So let's talk a little bit about those. So what I'm about to do for you here is I'm going to give you two equations, and I'm going to derive them from you. They both actually come from the ideal gas law. You don't have to derive them. All you have to do is you have to know the final result of that. And actually, if you write those down on your pair-out table up there at the top, I probably have to do that, right? But I'm going to derive them anyway, just because I can, and just to show you where they actually come from. So let's go here. So let's start out right here. So I know that PV is equal to nRT, right? Okay. Well, N is what? Well, that's your number of moles. Number of moles of gas, right? Okay. Well, how do I figure out the moles of something? Well, think about it this way. If I had 8 grams of helium, and I know that helium has a molar mass of 4 grams per mole, how many moles of helium do I have? Well, 8 grams, 4 grams per mole, 8 divided by 4, I've got 2 moles, right? So if I can take the mass of something and then put that over the molar mass, that's the same thing as the number of moles. So I'm going to take this equation and I'm going to replace this N with an M, which will be our mass, over MM, which will be our molar mass. And I get this, PV equals the M times over MM times R times T. All right. Well, notice what I've just done here. I've just introduced molar mass into this equation, which is kind of interesting. So tell you what, let's just solve for molar mass and let's see what this thing looks like. So I've got molar mass here in the denominator. I don't really want that. How do I get that out of there? Well, I can multiply both sides by molar mass, see, and that gets the molar mass out of the bottom. So if I do that, I get pressure times volume times molar mass is equal to mRT. Okay, well, if I want molar mass by itself, what would I do next? Well, I divide both sides by PV, and so therefore I end up with an equation that looks like this. The molar mass of a gas is equal to mRT over PV, and that's 1. Okay? Well, let's start here. So this is supposed to be an M up here, I guess. Molar mass is equal to mRT over PV. Okay, well, let's just move the pressure over here, just for fun. Okay, so to do that, I would multiply both sides by P. So that cancels that out. So I get pressure times molar mass is equal to mRT over V. All right, let's move the temperature over here as well. Why would I do that? Well, we're getting there. Okay, we'll talk about it. So let's move the temperature, and while we're at it, let's just move R over 2. Let's get that out of the way. So if I have mRT times V divided by V here, and I want to get the RT to the other side, I'm going to divide both sides by RT. All right, and that's what we have down here. I've flipped things. Well, I didn't actually. Yeah, I did. I flipped them here. So, but yeah, so there you go. So that gives me P times molar mass over RT. So what have I got over here left over? Well, I've still got the mass and I've still got the volume. Now, why would I want to do something like that? Well, because what is mass divided by volume? Well, that's density. So see, what I can do is I can take this mass over volume here. I can replace that with a little d, and that's density. And now I've got an equation that tells me the density of the gas. And so that equation looks like this. Density is equal to the pressure of the gas times its molar mass over R times T. And both of these equations are originally derived from the ideal gas law, but you don't have to derive them. If you can just know the boxed result there, then you're going to be fine. Okay? Okay, let's do a couple of problems here with these real quick. So what is the density of nitrogen gas at 27 degrees Celsius and 735 torr, or millimeters of mercury? Remember, those are the same thing. Okay, well, think about it. What are you mostly breathing in right now? Well, it's mostly nitrogen, right? 78% of the Earth's atmosphere is actually nitrogen. It's 72, 70 something here, maybe in the room you're watching this on or something like that. And the air pressure is probably a little bit less than sea level, so 735 torr, yeah, it's pretty close. So essentially, this is kind of a problem that's asking you, what is the density of air? At normal temperatures, normal pressure, something like that. A close approximation. All right, well, let's check it out. So which equation am I going to use? I would probably use the one with density in it if it were me. That's what I would do. So I know that density is equal to pressure times molar mass over RT. All right. Notice that R is in this equation. If R is in this equation, you have to use a certain set of units. You don't have a choice. R is equal to 0.0821 liter atmospheres over mole Kelvin. Again, that's a constant I would give you on a test. You're going to know that. It's going to just be so ingrained in your head by the time you get done with this, you won't be able to forget it. But it's going to be given to you anyway. All right. To know what units I need to use, look at the value for R. My volume has to be in liters, my pressure, atmospheres, in moles, and my temperature in Kelvin. All right. So do I know the pressure here of my nitrogen? Well, I know it's 735 torr. Can I leave it as 735 torr? No, my pressure has to be in atmospheres. Okay, so how do I convert from torr, or millimeter mercury, to atmospheres? Well, I know that 1 atmosphere is equal to 760 torr. All right, and that's a conversion factor that would be given to you on a test as well. All right, you just have to be able to use it. So 735 torr, I know 1 atmosphere is equal to 760 torr. Why'd I put the 1 here and the 760 here? So I could cancel out the torr, and I'm left with atmospheres. So 735 divided by 760, 0.967 atmospheres, that's my pressure. All right. What's that? Well, that's the molar mass. Okay, so I don't see the molar mass in this problem. Is there any way I could calculate it? Well, I know I've got N2 here. Can I calculate the molar mass of N2? Sure. It's 2 nitrogen atoms, and I know if I look in the periodic table that each nitrogen atom weighs, what, 14.01 roughly? So 14.01 times 2, that would be 28.02 grams per mole. All right. How about, we know R, how about the temperature? Well, it's 27 degrees Celsius. Can I leave it as 27 degrees Celsius? No, I need to change that to Kelvin. How do I change it to Kelvin? Add 273. So 27 plus 273 would be 300 Kelvin. All right, I've got everything over here in the proper units. Now I'm going to plug it into the equation, solve for D. So again, I'll put the units in. You don't have to. I'm just showing you how it cancels. 0.967 times 28.02 divided by 0.0821 times 300 Kelvin. All right, here's an atmosphere here in the top. Here's an atmosphere in the top half of this fraction. Those cancel. Here is a mole in the bottom half of this fraction on top. Here's a mole in the bottom half of this fraction on the bottom. Those cancel. Here's a Kelvin here. There's a Kelvin there, and those cancel. What are the only units I have left here? Well, I've got grams on top. I've got liters on the bottom, so what's going to be the units of my density? Grams per liter. All right, so 0.967 times 28.02, divide that by 0.0281, divide that again by 300, and you get roughly 1.10 grams per liter. And that would be the density of the nitrogen, which is, to a very first approximation, the density of the air around you. All right. Notice that liquids and solids tend to have densities on the gram per milliliter scale, whereas gases tend to have densities on the gram per liter scale. So gases are about 1,000 times less dense generally than solids and liquids. Those particles are very, very far apart, and that makes it extremely low density. So if I had a football and it wasn't aired up over here, and I had another football over here, and it was full of air, which one would weigh more? Well, the football with air would actually weigh more, but would it weigh that much more? Not that much more, because the density of air is only about 1 gram per milliliter. Excuse me, 1 gram per liter, not 1 gram per milliliter. All right, so gases have very, very low densities. This is why they're compressible. See, you can squish those molecules in there a little closer together. Okay? All right, well, here's another problem. A flask weighs 52.693 grams empty and 53.117 grams when filled with acetone vapor at 100 degrees Celsius and 752 torr. Taking the volume of the flask to be 226.2 milliliters, calculate the molar mass of acetone. So this is actually something you're going to do in lab if you haven't done it already. Okay, and this is fairly reasonable data. This is about a 200 milliliter flask. If you were using a 200 milliliter flask, 100 degrees, there's your water. This is roughly room pressure. So yeah, I mean, this is reasonable data for an actual lab if you were going to do it. All right. So you fill that flask with the acetone vapor. You raise the temperature up to 100 degrees. Okay, and room pressure roughly here. If your volume of your flask is this, what's the molar mass of the acetone? Okay, now, something important to note here. Do I have to know what's in acetone? Do I have to know the formula of the acetone? No. I don't have to know anything else about the acetone. See, if I had the formula of acetone, then it would be really, really easy to calculate the molar mass. I just add up the atoms there. Do I have to know the simplest formula of the acetone? Nope, don't have to know that. To find the molar mass of this gas, all I got to do is I got to convert it to a gas, because it's a gas law, not a liquid law. But if I can convert it to gas, I just have to know these 5 things. If I can figure out these 5 things, I can plug it in this equation, and I can get the molar mass knowing absolutely nothing about acetone. Well, fortunately, one of these things you already know, and that's R. And that's 0.0821 liter atmospheres over mole Kelvin. So, see, really all you need to know is 4 more things, and you can actually figure out the molar mass. All right, so there's R. Okay, well, what about the mass of the acetone? How am I going to figure that out? Well, I know that when I filled it with acetone vapor, it was 53.117 grams. So my acetone was what, 53.117 grams? No, that's how much the flask and the acetone weighed. So how could I figure out how much just the acetone weighed? Well, I know the flask weighs 52.693 grams empty. Couldn't I just subtract off the mass of the flask from the flask and the acetone, and wouldn't that just give me the acetone? Sure. So I've got 53.117 minus 52.693. So subtract that, 3 places past the decimal 3 here, 3 places past the decimal here, 3 places in my answer. Remember, addition, subtracting, you're looking places past the decimal point. 0.424 grams of acetone. Okay. Well, what else do I have here? Well, I got temperature. How do I figure out the temperature? Well, I know it's 100 degrees Celsius. Can I leave that in as 100? No, got to change it to Kelvin. Always got to change your temperatures to Kelvin here. So 100 plus 273, my temperature is 373 Kelvin. Okay. Pressure. Do we know the pressure of the acetone? Well, we know it's 752 torr. Can I leave it as 752 torr? No, because I'm using R in this equation, see? And when I'm using R in the equation, my pressure has to be in what? Atmospheres. So I know 1 atmosphere is equal to 760 torr. So do it this way. So your torrs cancel. 752 times 1 divided by 760, 0.989 atmospheres. All right. And then finally the volume. Do I know the volume? Well, I know the gas takes up the volume of the entire flask. And I know the flask is 226.2 milliliters, so that would be the volume of the gas. Can I leave it that way? No, because my volume has to be in what? Has to be in liters, because that's what it is up here in R. So to change it to liters, I could divide by 1,000, or I could do factor label, or I could just move my decimal 1, 2, 3 places this way, 0.2262 liters. All right? So now we have all the units over here, or all our variables over here in the units they need to be in. So we're going to plug them back in this big equation. Solve for molar mass. So 0.424 times 0.0821 times 373 divided by 989 times 0.2262. Okay, here's a atmosphere up here in the top half of this fraction. There's an atmosphere there. They cancel. Here is a liter up here. And here's a liter down here. Those cancel. Here's a Kelvin up here. Here's a Kelvin in the bottom half of this fraction on top. Those cancel as well. So the only units I have left is I have grams up here. And I have a 1 over moles here. So my units for my molar mass is going to be what? Grams per mole. See? That's why the units are there where they are. And that's why you have to get things in the proper units over here. You don't have to put that in. You just have to be able to make sure you get them in the units, and you can just put the numbers in. That's fine with me. All right. So we do the math, and we come up with 42.5 grams per mole. And there's your molar mass. Now notice you didn't have to know anything else about acetone except for this data up here, and you just found the molar mass. So why is that so useful? Well, if you'll remember, a long time ago we talked about doing simplest formulas. And remember, your simplest formula is your smallest whole number ratio of atoms to atoms in a compound. And then you had the molecular formula, and that was the true formula of the particular compound that you're dealing with. I can do the simplest formula from percent composition or analytical data, but to get from the simplest formula to the true formula, I needed to know one more piece of information. Do you happen to remember what that piece of information was? Anybody? Yeah, it was the molar mass. So if you had the simplest formula in the molar mass, you could figure out the true formula. Well, look, here's a way to figure out the molar mass of something without knowing anything about it. You don't even have to know the simplest formula to get the molar mass here. So you could figure out the simplest formula using the methods that we talked about before, and then you could figure out the molar mass using this, and you could put those together and you could actually get the true formula. All right. The formula for acetone is actually CH3C double bond O and then a CH3. Add all that up and you'll probably get something pretty close to 42.5 grams per mole. And that's what it is. So see, one way to find the molar mass of something, and I think I promised I'd tell you this too. See, I keep my promises. It's just a really long time coming sometimes. If I want to find the molar mass of something that is either a gas or it's very easily convertible into a gas, because I got to convert it to a gas. This is not a liquid law. This is a gas law. This is one way I can do it experimentally. See. Now, what if I have a liquid or a solid that I can't convert into a gas? Can I do it this way? No, because it's a gas law. Are there ways to find the molar masses of liquids and solids, even if you don't know the simplest formula? There are ways. You'll do one next semester, but not this semester. But yep, that's how it works. Know the equation, get everything in the proper units, plug it in. Got to be in certain units because R is in the equation. That's the key. Make sense? All right, and those are two equations that you can use that are similar here to the ideal gas law, or derived from the ideal gas law, actually. Okay, well, let's move on. Let's talk about volumes of gases involved in reactions. Remember Chapter 3 and Chapter 4? Remember all that stoichiometry you did? Remember all that fun stuff? And I said you really need to know how to do stoichiometry, because it turns out that pretty much every chapter has its own little version of Chapter 3 and 4, the stoichiometry stuff. Well, Chapter 9 is no exception. Here it is right here. Volumes of gases involved in reactions. All right. When you're dealing with gases, because they don't weigh a lot, and because you can't really put them on the scale and weigh them because they tend to float off on you, it is more convenient sometimes to deal with volume of gas instead of moles of gas or mass of gas. All right. So let's say, for example, I'm doing this little reaction, which is something you actually have already done in the lab. I can take a piece of zinc and I can put that in some hydrochloric acid. All right. And the zinc will disappear and I'll see bubbles everywhere. What are the bubbles? Well, that's hydrogen gas, that's being evolved. Why is the zinc disappearing? Well, because it's dissolving. It's going into solution and forming the zinc 2+ ion. So, yes, this is an oxidation reduction reaction. I'll let you figure out which is which. But yeah, you've done this in the laboratory. You've seen this. Okay? So, given this equation, I went ahead and balanced it for you because I'm such a nice teacher. You could have done it anyway. Given the above equation, calculate the mass of zinc required to form 16 liters of hydrogen gas at 20 degrees Celsius, 735 torr. Okay. Well, you'll remember we gave you a little path to follow on your stoichiometry, grams of A to moles of A to moles of B to grams of B. Remember our little roadmap? Well, here's the path you're going to follow on this one. You're given liters of hydrogen. You're going to go to moles of hydrogen. If you can make it to moles of hydrogen, you can make it to moles of zinc. And if you can get to moles of zinc, you can get to grams of zinc. 2/3 of this problem is stuff you already know how to do. This is stuff you've already done. The only tricky part is this right here. All right? So how do I get from liters of a gas to moles of a gas? I mean, I could get from liters of solution to moles of solution using the molarity. But this is not a concentration thing. This is liters of a gas to moles of a gas, or moles of a gas to liters of a gas. Well, notice this. 20 degrees Celsius, 735 torr. See how they just kind of threw that in there at the end? Like it's not really important. Given the above equation, calculate the mass of zinc required to form 16 liters of hydrogen gas at 20 degrees Celsius, 735 torr. Is it really just kind of useless information? No. They gave you that temperature and they gave you that pressure for a reason. All right, and here's why. If I want to go from liters of a gas to moles of a gas, or moles of a gas to liters of a gas, I'm going to use PV equals nRT. That's the equation I'm going to use to find the necessary relation. All right, so in this case, I'm given 16 liters of hydrogen, and I want to get to moles of hydrogen. So I'm going to take this equation here. Where's moles in this equation? Well, look at there. See, there's moles right there. So I'm going to solve this equation for moles. So I'm going to divide both sides by RT. So N is equal to PV over RT. Just divide both sides by RT. So if I can find the pressure of my hydrogen, the volume of my hydrogen, R and T, I can plug those in, and I can figure the number of moles. Make sense? Okay, well, R is in this equation. Do I have to use a certain set of units? Yes, I do. So here's R. That's 0.0821 liter atmospheres mole Kelvin. Okay, so do I know the pressure of the hydrogen? Yeah, it's 735 torr. They gave me that. So 735 torr. Need to change that to atmospheres. So 1 atmosphere, 760 torr, 0.967 atmospheres. Okay. Do I know the volume of the hydrogen? Yes, I know it's 16 liters. They give me that in the problem. Can I leave it as 16 liters? Yes, I can leave it as 16 liters. Okay. Do I know the temperature? Well, I know it's 20 degrees Celsius. See? Can I leave it as 20 degrees Celsius? No, I got to change that to Kelvin. So you're going to add 273, and so my temperature is 293 Kelvin. So I'm going to take all these values. I'm going to plug them into this equation. 0.967 times 16 divided by 0.0821 times 293, and I get 0.643 moles of hydrogen gas. See, anytime you need to go from liters of a gas to moles of a gas, PV equals nRT. See, here's your liters. That's your volume. There's your moles. So if you need no moles, solve for N. If you were given the number of moles and you were trying to figure out how many liters of hydrogen gas you were producing or something like that, well, then you do the same thing. You just solve for volume. And you divide both sides by P, and so nRT over P would be equal to volume. Solve for volume. But see, this stuff right here that they just kind of threw in at the end is kind of a tagline there. They tried to sneak it by you. It's important because, look, if you don't know the temperature and you don't know the pressure, you can't use this equation. So if you're doing stoichiometry type problems and they give you a pressure and a temperature in there, or they say at room temperature and pressure, or if they say at STP, standard temperature and pressure, which of course is what? 0 degrees Celsius, 1 atmosphere. Okay, standard temperature and pressure. Okay. If they give you that, little red flag ought to go up in your head and say, this might be a gas stoichiometry problem, because otherwise they wouldn't give me that pressure and that temperature. And you need that to do this. All right, so use the ideal gas law to get your number of moles. Once you got the number of moles, this is just a straight chapter 4 problem. I've got 0.643 moles of hydrogen. How do I get to moles of zinc? How do I get from moles of something to moles of something else? Use your coefficient, your balanced equation. So for every 1 mole of, I can produce 1 mole of hydrogen from every 1 mole of zinc that I start with. Coefficient's your balanced equation. Hydrogen goes on bottom, zinc on top, so your hydrogen cancels. 1 mole of zinc, 1 mole of hydrogen. Okay, but I want mass of hydrogen. I want grams of hydrogen. How do I go from moles of zinc, grams of zinc? How do I go from moles of zinc to grams of zinc? What do I use? I use the molar mass. So I look that up in the periodic table, and 1 mole of zinc weighs 65.39 grams. Moles on bottom, so they cancel. What's the only units I have left here? grams of zinc, 42.0 grams of zinc required to produce 16 liters of hydrogen at 20 degrees Celsius and 735 torr. Do you see that this problem is just a chapter 4 problem? It's stuff you already know how to do. I told you you need to know how to do this, or your life would be incredibly, incredibly difficult in this class from here on out. Well, see, I mean, you saw it in the thermo chapter, now you're seeing it again. Yeah, it'll pop up again, all this stuff. You got to be able to do that. The only thing that's really new here is this over here. And basically, if you need to go from liters to moles or moles to liters, use your ideal gas law. Okay? So, in summary, if I need to go from moles of something to atoms of something, what do I use? I use Avogadro's number, 6.022 times 10 to the 23rd. If I need to go from moles of something to grams of something, what do I use? Well, I use the molar mass, in the periodic table. If I need to go from moles of something to moles of something else, what do I use? I use my coefficients in my balanced equation. If I need to go from moles of a solute to liters of solution, or liters of solution to moles of a solute, what do I use? I use the molarity to get me there. If I need to go from moles of something to kilojoules of heat given off or taken in, or kilojoules of heat to moles, what do I use? I use the coefficients in my balanced thermochemical equation, chapter 5. And then if I need to go from liters of a gas to moles of a gas, or moles of a gas to liters of a gas, what do I use? Use the ideal gas law here to get you where you need to go. Because there's your volume, see, and there's your moles. Solve for what you don't know, plug everything in, get the value. And that's this. But really, everything past this is chapter 4 stuff. You can already do this. This is the only thing that's new. All right? Okay. Sick of talking about the ideal gas law? Okay, well, let's talk about something else. Ideal gas law is not the only gas law in town. There are others. So let's talk about something called Dalton's Law real quick here. Dalton's Law. What is Dalton's Law? Well, Dalton's Law deals with gas mixtures. Can you think of a particular gas mixture that you happen to run into every day? It's right under your nose. It's in your nose. Well, air. Air is a gas mixture. There is no such thing as an air molecule. Ar is not air in the periodic table. That's argon. It's mostly nitrogen, about 78%, roughly. Roughly 21% oxygen. Actually, about 1% argon. That's the next most plentiful gas in the atmosphere. And this is, discounting water vapor. Water vapor can be anywhere from, probably 0% to about 4% by mass. Depends on where you are. 4% in a rainforest and 0% out here. But if you're talking about dry air, that's pretty much roughly the percentages there. And so, yeah, that's a gas mixture. All right, and that's what Dalton's Law deals with. Dalton's Law says the total pressure of a gas mixture is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3 plus how many ever gases I have. Okay, now don't get too freaked out about this partial pressure stuff. Okay, partial pressure just means, let's say for example I had a tire and I've got that air in the tire. And let's say that I found a way to take out everything but the nitrogen. And I left the nitrogen in there. All right. If I remeasured the pressure of the tire at that point, whatever pressure I get, that's the partial pressure of the nitrogen. If I had taken the air in the tire and I found a way to take out everything but the oxygen, remeasured the pressure of the tire, that's the partial pressure of the oxygen. So it's basically the pressure contribution of that particular gas to the entire total mixture. That's what partial pressure means. All right. Well, really, ultimately, what Dalton's Law really says in the grand scheme of things is a mole of gas is a mole of gas. It really doesn't matter what it is. It really matters how much. If I got 2 moles of nitrogen and 1 mole of oxygen, those pressures that they're exerting are additive. I could have 2 moles of nitrogen, 1 mole of oxygen, or I could have 3 moles of nitrogen. It doesn't really matter. You're still going to get exactly the same pressure. That's ultimately what Dalton's Law really says. All right. Now, where would I ever use something like this? Well, quite often we use it to collect gases over water. Used to do this little experiment with the intro to chemistry kids where we made oxygen. We took some hydrogen peroxide and put just a pinch of manganese dioxide in a test tube that was kind of sealed up with a little tube coming out of it. And you saw bubbles, and that was actually oxygen gas. So you take those bubbles, you take them, they go through a rubber tube, and you stick them in a bottle. Well, the problem is, if I got a bottle sitting over here, how do I know when the bottle is full of oxygen? Because I can't see the oxygen. It looks the same as air, right? So what you do is you actually run that tube underneath the water, and then you fill a tray full of water, and you put a bottle, and you fill it up with water, but you turn it upside down. And then you put the hose up in there like that. And so what happens as your gas comes through, it will bubble up into the bottle. It'll get trapped there in the bottle. And the bottle looks like it's emptying. And that's because the gas is actually pushing the water out. And eventually you'll get to a point where your bottle looks totally empty. And there's like bubbles coming out the bottom here. Okay, so is my bottle really empty? Well, no, it's actually full of oxygen gas there. So now I place a little cover slip under that bottle and I turn it back over and I got myself a bottle of oxygen. See? And that's how you do it without getting the other gases in there. Well, that's what we tell the intro to chemistry kids. And, you know, whatever else is in there is not reacting with what we're going to do next. So it's not really that big a deal, I suppose. But technically that's not quite true. We're leaving something out there. Kind of makes you wonder what I'm not telling you, right? So what's the deal? Well, you're collecting that gas over water, and water has a certain what we call vapor pressure. And vapor pressure is the tendency for a liquid to evaporate. We'll go there until we get to chapter 10. Okay, so it'll evaporate. And vapor pressure depends on temperature. You know, hot tea evaporates faster than cold tea. And it depends on the liquid. All right, so you've got water in there underneath the bottle, and that's evaporating. And so really what you have in the bottle is you have oxygen, but you've also got some water vapor in there as well. Right? So the total pressure of the gas is equal to, or the pressure of the oxygen, let's say, if I'm collecting oxygen here, is really equal to the total pressure inside the bottle minus the pressure of the water vapor in there. And that is something that has been studied quite a bit, and I can look up the vapor pressure of the water in a chart at the specified temperature, subtract that off, whatever's left over must be the oxygen. And that's really technically the pressure of the oxygen in the bottle. Make sense? And so that's one place we would use this in the laboratory. Here's another little equation that kind of comes in handy. The pressure contribution of a particular gas is equal to x1 times P total, where x1 is something called the mole fraction of the gas in the mixture. And mole fraction is pretty much exactly kind of what it says. It's the moles of gas that you're looking at over the total moles of gas in the mixture. Mole fraction. Notice it's a lot like percent. You're just not multiplying by 100. And so this is another concentration unit. Mole fraction. Mole fractions have no units because they're essentially fractions, like 1/3 or 1/2 or something like that. They're just a number or a fraction if you want to leave it as a fraction or something like that. Okay? So, for example, a tank contains 3 moles of oxygen, 6.5 moles of helium, and 10 moles of argon. The total pressure in the tank at a given temperature is 1500 torr. What are the partial pressures of each of the gases in the tank? Okay, well, I know that the partial pressure of my gas is equal to its mole fraction times the total. So if I can find the mole fraction here, I know the total pressure. I can just plug that in this little equation here. So let's start with the oxygen. How do I find the mole fraction of the oxygen? Well, how many moles of oxygen do I have? Well, I have 3. How many moles total do I have in the tank? Well, I've got 10 and 6.5, that's 16.5, plus the 3. I have 19.5 moles total in the tank. It's not moles of what you're interested in over moles of everything else. It's moles of what you're interested in over moles of everything. Don't forget to add that 3 in there. You know, if I have 30 red marbles in a box of 100 marbles, what percent of my marbles are red? Well, 30 over 100 times 100, 30%. Not 30 over 70, 30 over 100. The easiest way to miss that problem. Don't do that. Okay, so 3 divided by 19.5, 0.15. And notice my moles cancel. There's no units here. That's the mole fraction, 0.15. All right, how about the helium? Well, I know I've got 6.5 moles of helium over my total of 19.5 moles. So the mole fraction there is 0.33. All right, argon, 10 moles of argon over 19.5, 0.51. Notice your mole fractions will be anywhere between 0 and 1, just like your percentages are between 0 and 100. See, you're not multiplying by 100 here. That's what makes it a mole fraction instead of a mole percent. Okay, so if I want to know the partial pressure of the oxygen, well, that's the mole fraction of the oxygen, 0.15, times the total pressure, 1,500, 225 torr. If I want to know the partial pressure of the helium, well, that's the mole fraction of the helium, 0.33, times the total pressure, 1,500 torr, 495 torr. Mole fraction of the argon, 0.15, times 1,500, 765 torr. And that's the partial pressure of the argon. All right. So what does this mean here? Well, this means if I took the oxygen and the helium out of the tank and just left the argon in there, the pressure would only be 765 torr. It wouldn't be 1,500 torr. That's what partial pressure means. All right. Now notice something here. As far as the moles go, how much of my total moles here is actually argon? Well, about half, right? So how much pressure is exerted by the argon of the total 1,500? About half. A third of my moles are actually helium, so it contributes how much to the total pressure? About a third as much. All right. A mole of gas is a mole of gas. If I have a lot of moles of gas, it's going to exert a lot of pressure. If I have a little moles of gas of something else, it's going to exert a little bit more. But if I put them both in the same container, I just simply add the pressures up, and that's my total pressure. See? And notice that 225 plus 495 plus 765 is what? 1,500 torr. Because the total pressure in a gas mixture is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3. And that's how it works. Make sense? Can you do this? If you can do this, that's pretty much all I'm probably going to give you on Dalton's Law. If you can do that, then I think we're cool on Dalton's Law. All right? Okay. Well, almost there. So one last thing we need to talk about, and well, actually two last things. But kinetic theory of gases. So we're going to save that for the next video. We'll talk about that. And then I really think I could finish this in one more. So I think we can actually finish chapter 9 in one more video. So almost there. Hang in there. So we'll see you next time. Bye.